Hey guys, we're going to look at some ideas of sets, or set theory, which is called set operations. These are very important to know, not too hard to grasp, but I'm just going to go over a few examples, so let's get started. Alright, so in particular we want to look at union and intersection, difference, and what we call set complement. And if we use Venn diagrams, which you should get comfortable with, it makes these concepts pretty clear. So let me show you what those look like. Okay, with set union, I'm going to take two sets, let's call them A and B. So what I want with A union B is all the stuff that's in either A or B. Okay, so when you say A union B, and we write it like this with like a capital U, the way you want to think about this is A or B. The things that are in A or the things that are in B. So here are the things that are in A. Here are the things that are in B. And I want the thing that's in either A or B. So if the thing is in A, that's good, I want it. If the thing's in B, that's great, I want it. If it's in both, awesome, I want that as well. All right, A or B, A union B means all that, okay? It's A or B. If I want A intersect B, we write it like this, like kind of like an upside down U. This is A and B. So this time, I want the things, the requirement is it has to be in both things. It has to be in A and it has to be in B. These are the things that are in both A and B. And so when I say A intersect B, that's exactly what I want. All right, and we'll do some examples covering these ideas. Okay, so how about difference? So I might write this like A minus B, depending on your book. Some books write it like A, it looks like a backslash B. They mean the same thing. And so we mean the set difference. What we mean is the things that are in A, but not in B. Okay, so let me think. All right, so these are the things in A here, but this little tiny part in the middle are also in B. So when I want A subtract B, actually I want that part cut off. So this is the set difference. You can say A minus B is one way to read this, but A minus B, A throw away B, A subtract B is this green region. We're throwing out the intersection really away from A. Okay, now the last one, complement. So this one we might write as like it looks like A to the C power. I've also seen it as A prime. I've also seen it written as like A with a bar over it. And what we mean by this is we take two sets. Okay, we have A and B. And actually we don't need B in this context. What we need is something outside of A. We need some sort of universal set. So everything that could possibly be considered that A and B are in, or their environment. And so when I say A complement, what I mean is the stuff that is not in A. So the things that are not in A. So all this counts. Yeah, I want the stuff that's in B because that's not in A, as long as it's not in the intersection. So I want all this rectangular region except for A, right? So that's the part I want to leave out. These four concepts are not in themselves too difficult, but we do want to look at some examples on how to figure out what are in these sets. So let's take a look at that. All right, so here we have some sort of universal set 1 through 10. And so all we're considering now are integers 1 through 10. Okay, now we have set A, looks like my even numbers. Set B, we have 6, 7, 8, 9. C is 2, 3, 5, 7. I want to find the following. I want to find A union B. Remember, the union means the things that are in A or B. Okay, so here that means all the stuff that's in A, 2, 4, 6, 8, 10. Also the stuff that's in B. 6 we've already counted. 7 and 9 we need to throw in there. So you know what I'm going to do? I'm going to write them in order. Maybe it's a little OCD that way. But we want 2, 4, 6, 7, 8, 9, 10. There's my A union B. And so in my head, I'm thinking I am counting the stuff that's in A or B. Okay. B intersect C. So now this time, intersection means the stuff that's in both. It has to be B and C. So these guys are the things that are in both B and C. So if I'm looking at B and C, comparing, let's see, 6 is not in both, 7 is, 8 and 9 are not, 2, 3, and 5 are not in both. The only thing that's in both is 7. All right, now I think a good way of picturing this let's see. So we have 6, 7, 8, 9. There's set B. 2, 3, 5, 7. There's set C. The only thing that's in both was the 7. Right? So here's B and here's C. I hope that makes sense. Let's look at part C here. We have A set difference C, or A throw away C. So this time I'm taking the set A and I'm deleting the things that are in C away from set A. Alright, so let me think. So that means the stuff that's in A, but it's also in C, I'm going to delete that out. So it looks like the 2 is in both, so I'm going to delete that. But I think everything else in A has nothing to do with C. So that's what we want. Now I can draw a picture of it, just kind of make sense of it a little bit. A and C. So the 2 was in both, and then the rest of A had nothing to do with C. So as I delete the 2, I just have the remainder of A. I can do a similar thing with A throw away C. This time I want this part of C. Alright, so, and again, C is 2, 3, 5, 7. So if I delete A away from that, the only thing that gets deleted is the 2. So I have 3, 5, 7. Great. Okay. Let's look at E. It says this time we want C throw away A complement. Okay. What does that mean? That means the stuff that's in C throw out A are the things I don't want. So I want everything but C delete A. And now I'm talking about my universal set here, which was 1 through 10. So thankfully in D part I already found C throw out A. So I want the stuff 1 through 10 that's not in C throw out A. Okay, so that means I want 1, 2. I don't want 3 because 3 is in this set up here. Okay, does it make sense? 4, 5, don't want 5. 6, don't want 7. 8, 9, 10. Okay, there we go. There is the stuff that's in my universal set that's not in C throw out A, or C minus A. Okay, let's try that again. So this time I want to find the complement of A union B union C. So now I have 3 sets, A union B, or A, B, and C. I want to find their union, which would be all of this stuff, because what I actually want is the complement of that. I want the stuff outside of this set. Okay. So in other words, the stuff that's in 1 through 10 that's not in any of A, B, or C. That's what we're trying to find here, right? We're trying to find the stuff in no man's land. Okay, so let's look again. Let's look at our 3 sets again. I'm going to do a little scratch up here. If I had A union B union C, what do I get? Let's see. 2. Is there a 3 in any of these? Yes, there's a 3 in C. Is there a 4? Yeah, A. Is there a 5? Yes, in C. C has a 5. B has 6, 7, 8, 9, and A has 10. And so that's A union B union C. What is not in any of those? The complement of A union B union C then is just 1. Because that's the only thing in my universal set that wasn't in either A, B, or C. I hope that makes sense. Alright, let me give you another example here. And we're going to do something a little unusual, but we're going to look at a really big intersection or really big unions. We just saw an example where we had A union B union C. What about like an infinite number of unions or infinite number of intersections? Can we do that? Yeah, of course we can. I mean, this is mathematics, right? So actually, I got a few little typos here I need to fix. So in this particular example, I'm going to start with I equals 1, 1 over I. I'll explain what that means in a little bit, and we'll do the same thing for part B as well. So you see like this giant intersection. I'm going to do the intersection of a bunch of stuff, and the things I'm intersecting look like this: 0 to 1 over I, where the first one is when I equals 1, the second one is I equals 2, the third one is when I equals 3, and we keep going out, all the way out to infinity. So if I'm trying to think like what that looks like, I mean, what is 0 to 1 over I? What does that look like? This is an interval, okay? So I could draw a number line, and I'm starting at 0, and I'm going out to 1 over I, whatever that is. And my interval is all the stuff including the endpoints 0 and 1 over I. So for example, if I said the first one is 0 to 1. All right, so I guess you could write this like this. 0 to 1, that's the first one. We want to intersect that with 0 to, when I is 2, we get 1/2. Okay, I want to intersect that with 0 to 1/3. And I want to keep doing this. Keep intersecting all of them. Now remember, the intersection is what's in everything. So notice if I had like a number line here. So first I said 0 to 1. Okay. And then I said 0 to 1/2. So if I just do the intersection of those two, what's in both parts? Well, just the 0 to 1/2, right? That's the part that's in both. And then if I do 0 to 1 intersect 0 to 1/2 intersect 0 to 1/3, I get what's in all three of those. 0 to 1/3 is in all three of those sets. So what about if I keep doing this? Like I go out to 0, 1, intersect 0 to 1/2, intersect all the way up to 0 to 1,000th. What do I get? I get just 0 to 1,000th. And as this I keeps getting bigger and bigger and bigger, those little intervals get smaller and smaller and smaller, and I'm intersecting all of them. So the only thing that's in all of these, when I go out to infinity, what's in the middle of all this would just be 0. 0 is going to be the only number in every single one of these sets. Okay, that's weird. That's conceptually weird. And that's okay. That's weird, but it's okay. Let's look at part B. This time we're doing the same thing, but we're doing infinite union. So let me think. If I had I equals 1, I get 0 to 1 minus 1, which is 0 to 0. Intersect 0 to, let's see, when I is 2, we get 1 minus 1/2, so that's 0 to 1/2. This time we're not doing intersect, we're doing union, right? Union, 0 to, okay, when I is 2, when I is 3, I get 1 minus 1/3, so I go to 2/3. And then I think if I is 4, I get 0 to 3/4. And we keep doing this. Okay, we go out to infinity. So if I'm looking on my map here, my number line, I started out with just going 0, then 0 to 1/2. I want all that. Union, so this is in either or both. I go out to 2/3. Okay, and I want all of that. And then I union that with 3/4. I union that with 4/5, and 5/6 and 6/7, and so on and so on. So as I keep unioning these things together, what do I end up with? Well, these points, what I said at 3/4, 4/5, 5/6, these are getting closer and closer to the number 1. Okay, so as I union all these together, I'm actually going to end up with 0 to 1. Now, I understand this is an unusual example, but I'm just trying to show you how powerful union and intersection can be. We can even extend it to an infinite number of sets that we're unioning and intersecting together. Guys, I hope this makes sense, especially in example 1 like we have here, where we're trying to just identify what's in the union and intersection, set complement, that kind of thing, set difference. If you have questions, please let me know. I'd be happy to help. This is very, very powerful stuff, and you can do it. I know you can do it because this is just math. Hope you guys have a great day, and thanks for watching.